everybody, welcome back to Unit 5 from the OpenStack Psychology 2E lecture slides. My name is Prescott. I'm here at PsychSyncs, the Sync Psychology, and we're going to be continuing where we left off. Last time we talked about sensation and perception. We started to go over amplitude and wavelength. Again, amplitude is the height from the peak to the trough of each wave, and then wavelength is the distance from each peak of the individual waves. So we're going to continue from there and start talking about frequency. So wavelength is directly related to frequency. Frequency is the number of waves that pass a given point in a given time period and is expressed in hertz or Hz. So longer wavelengths have lower frequencies and shorter wavelengths have higher frequencies. So this figure illustrates waves of differing wavelengths/frequencies. At the top of the figure, the red wave has a long wavelength and short frequency. So you can see how long the wavelengths are. So moving from the top to the bottom, the wavelengths decrease and frequencies increase. So by the time you get to the blue right there, you can see how frequent the wavelengths are. So light waves. The visible spectrum is the portion of the electromagnetic spectrum that we can see. So different species can see different portions of the spectrum. Humans can see wavelengths ranging from about 380 to 740 nm. So see here, nice graph, wavelength, frequency, and tells you about the size. So here we have atomic nuclei, which obviously humans can't see, unless you're Superman or something. Then we have atoms, X-ray wavelengths, molecules, ultraviolet, protozoans, or is where visible is, pinpoints, infrared, honeybees, and then humans and buildings. So I don't know if it's saying that pinpoints, like a small, it looks like a needle or button. So this is about where we can start to see. So these are wavelengths that we can perceive. We can't see molecules and atoms. So figure 5.6, light as visible to humans makes up only a small portion of the electromagnetic spectrum. Again, we're kind of all the way down here when there's all this stuff. So perception of color. Wavelength and color. Different wavelengths of light are associated with our perception of different colors. So longer wavelengths equal reds, and intermediate wavelengths are greens, and shorter wavelengths are blues and violets. So the amplitude of light waves is associated with brightness/intensity of color, so larger amplitudes appear brighter. Going on from light waves, we have sound waves. So frequency of sound waves equals the pitch. So high frequency equals high pitched sound. Low frequency equals low pitched sound. The audible range of sound frequencies in humans is between 20 and 2,000 hertz. So amplitude in decibels. So the amplitude of sound waves equals loudness. Higher amplitude, louder sounds. Lower amplitude, quieter sounds. So loudness is measured in decibels, dB. So a typical conversation is about 60 decibels. Rock concert about 120 decibels. The potential for hearing damage is 80 to 130 decibels. So if you go to a rock concert, you might get some hearing damage. And the threshold for pain is 130 decibels. So continuing with sound waves, we have a nice chart here. This figure illustrates the loudness of common sound. So your hearing threshold obviously would start at 0, and it goes all the way up in each picture. Cars at 80 decibels, river running is 20 decibels, whisper about 30, soft music 40, and it goes up to, here's your risk of hearing loss, again at 130, to rock concert, to jets flying overhead is the same as the pain threshold. And at 140 decibels is when it's just harmful for your hearing and your ears. Next, we have vision. So our eyes take in sensory information that helps us to understand the world around us. So nice bunch of pictures of eyes. We will go into, no, we got plenty of time. I don't know why I thought we were going for so long. So continuing with the visual system, the anatomy of the visual system. So light waves are transmitted across the cornea and enter through the pupil. The pupil size, so here you go, pupil, is controlled by muscles that are connected to the iris, the colored part of the eye. So I have, like greenish blue eyes. So that's the color of your eyes is your iris. Anyways, the light crosses the lens right here and is focused on the fovea, which is part of the retina. So the fovea contains photoreceptors. Photoreceptors are connected to the retinal ganglion cells. Axons from these cells exit through the back of the eye where they form the optic nerve. The optic nerve then carries the visual information to the brain. So that's how the visual system works. It goes from pupil all the way to optical nerve. So blind spot is a point of no receptors where information exits the eye where we cannot respond to visual information. And I actually saw this cool thing on Instagram where it was like 3 dots and the middle dot was red, and it was like, oh, this will show you your eye's blind spot. Focus on the black dot for 30 seconds and then move in closely, the phone close to your face, and the red spot disappeared. Like I couldn't see it anymore, even though I knew it was right there. It was really cool. So that's a blind spot. So we have a more in-depth look at the visual system. Kind of nasty. Next, we have photoreceptors. So photoreceptors, cones, which are phototopic or daytime vision, work best in bright light conditions. Obviously, daytime, normally bright. It has high acuity color information and is located in the fovea. Now, rods are scotopic or nighttime vision, and they work best in low light conditions. They have high sensitivity and allows for low acuity vision in dim light. And it is involved in the perception of movement in our peripheral vision. So it's located in the periphery, the edge of the retina. So the 2 types of photoreceptors are shown in this image. Rods are colored green and cones are blue. So here you go, rods and cones. Next, we have the optic chiasm. The optic nerve of each eye merges at the optic chiasm, an X-shaped structure just below the cerebral cortex. So information from the right visual field is sent to the left hemisphere, and information from the left visual field is sent to the right hemisphere. This information is then sent to the occipital lobe for processing. So this illustration shows the optic chiasm at the front of the brain and the pathways to the occipital lobe at the back of the brain, where visual sensations are processed into meaningful perception. So see the eye, right eye, is absorbing light information, so it goes to the left hemisphere and vice versa for the left eye, and those go to the occipital lobe where your visual sensations, so what you see are processed into meaningful perceptions, which could, for example, with this process, you see a line, it goes through your optic chiasm to the occipital lobe, and then you process that into a meaningful perception, which is, oh crap, there's a line right in front of me. So it's a little example. So visual pathways. After being processed in the occipital lobe, visual information exits and goes through 2 different pathways. So we have the what pathway, which is object recognition and object identification, and the where/how pathway, so location in space and how one might interact with a particular visual stimulus. So, color vision. So you have 2 theories for color vision. The trichromatic theory of color vision, which is all colors can be produced by combining red, green, and blue. It applies to the retina, where color vision is controlled by 3 types of cones. So, opponent process theory. Color is coded in opponent pairs. So, black and white, yellow and blue, green and red. Some cells are excited by one of the opponent colors and are inhibited by the other. And this applies to cells after the retina. Research has found that both theories are true, but for different parts of the visual system. So, this figure illustrates the different sensitivities for the 3 cone types found in a normal-sighted individual. So, there you go there, that's color vision. Now, here we have support for the opponent process theory. So, when staring at a colored stimulus, the color pairings of the opponent process theory lead to a negative afterimage. So, an afterimage is a continuation of a visual sensation after removal of the stimulus. So, stare at the white dot, this little fun thing you can do. So stare at the white dot for 30 to 60 seconds, and then move your eyes to a blank piece of white paper. What do you see? And if you guys want, you can leave in the comments, what do you see? I didn't do it myself, and I'm not going to because I don't want to just be staring for 30 seconds to a minute. So if you guys are interested, you can do that. So next we have depth perception. Now depth perception is our ability to perceive spatial relationships in 3D. So depth cues of a visual scene are used to establish our sense of depth. So depth cues are, you have binocular cues, or cues that rely on the use of both eyes, so bi, two. So binocular disparity, slightly different view of the world that each eye receives. And then you have monocular cues, cues that rely on only one eye, so mono, one. So you have a linear perspective is when two parallel lines seem to converge, and interposition, the partial overlap of objects. So here's an example. We perceive depth in a two-dimensional figure like this one through the use of monocular cues like linear perspective, again, when two parallel lines seem to converge. And so, like the parallel lines converging as the road narrows in the distance. And so that's how we're able to perceive depth in this picture, because we see these two parallel lines getting closer together. We're able to tell, oh, that's in the background. And here we have a little, I don't know if you've ever seen this, but it's a little like test of colorblindness, and it's, can you distinguish the numbers in the middle of all these dots that are different colors from the background, the rest of the dots. So here you have, well, I don't want to spoil it for you, but yeah, if you can't if you can't see the numbers in the center, you might have some kind of color blindness. Fun fact. Next, we have, we'll go through the auditory system in the next video. Again, my name is Prescott here at PsychSyncs, the Sync Psychology, and we are going to continue going through the OpenStack Psychology 2E lecture slides in the next video. I hope you guys enjoyed, and I will see you in the next video. Thanks, bye.